Okay, now that we know how to visualize what convergence looks like, we are going to discuss the number of theorems we have to actually prove if something is convergent. And before we can actually do that, we need to talk about the different ways in which a power series can converge. So this is the convergence theorem for power series, and it outlines three different possibilities. We're going to define our power series to be the sum from n equals 0 to infinity of some sequence c sub n times the quantity x minus a to the n power. And again, this is some power series centered at x equals a, and what we're going to do is recognize that eventually we can show that something is divergent if the power series, if the distance between x and a is greater than r, and this is going to be for a divergent power series. But for convergence, if the distance between x and a is somewhere less than the order of r, then we are convergent. The series may or may not converge at the endpoints, and that's actually what we're going to discuss in future lessons. Of course, then we have two other possibilities where the series converges for all x, and in that case, r would be infinity, and we have seen some Taylor series, as is cosine and sine, that are convergent for all x. And the third possibility is that the series converges at x equals a, at a single point. In that case, r is 0. And it kind of brings about this question, what is r? So in English, power series can converge on an interval, which we have discussed in the past, everywhere or only at one value. And that's really what that theorem was just stating. We refer to r as the radius of convergence, which brings about a definition. We're going to talk about the number r is the radius of convergence, and the set of all values of x for which the series converges is called the interval of convergence. And now what we're going to do is really discuss the different theorems that we have that will help us determine if a power series converges or diverges. One that we have discussed in the past is that if we have a power series starting at n equals 0 and going towards infinity, of course, of a sequence, if the limit as n goes to infinity of that sequence is 0, then we know that the power series of the sequence would then be convergent. So let's formalize that. If the power series of a sequence a sub n it diverges if the limit then either fails to exist or is different than 0. And that is really just saying the same thing as if the limit of that sequence as n goes to infinity is 0, then it is also convergent. Now we're going to discuss three more theorems, and the first being the direct comparison test. And we have talked a number of times about comparisons, and so let's just build a couple of tools here so we can discuss this theorem a little more. So we have the direct comparison test, and what we have is a series of a sequence, and it's going to have no negative terms. So we have two different cases to consider. One is the convergent, and another one is a divergent scenario. So first, the convergent. If the series of the sequence a sub n converges if there is a power series, and we're going to denote that with a series of c sub n, with a sub n less than or equal to this convergent series c sub n for all n greater than some integer capital N. And what that means is that eventually, if our sequence becomes less than and always less than or equal to this convergent sequence, then we know that it also converges as well. Now we're going to discuss the case for a divergent series, and we're still discussing a sub n here, and it's divergent if there exists a power series d sub n, d for divergent, with a sub n greater than or equal to d sub n for all n greater than n, and of course we're still discussing some integer n. And what this is saying is that if we know that a power series diverges, and the one we're referring to, a sub n, is always greater than or equal to a divergent series eventually, then it is also going to become divergent. So really what this capital N does is it just ensures that eventually one series dominates another. And what we're going to do in the next video is discuss how we can use this in an example to prove the convergence or divergence of a power series.